Okay, we spent quite a bit of time just talking about getting the area under this curve. We talked about how we could approach estimating it, then we talked about summation formulas, then we actually did estimate it, and in fact, let me just write that up in the corner here, what our estimate was. Our estimate from the last video was 94 over 64. That was our estimate for this area. Okay. And now finally let's talk about getting the exact area. And it's really not going to be very much different from the last video. It's going to be very, very similar. So let's see. The width of each rectangle. Well, we know that the more rectangles we use, the better our estimate gets. So maybe we want to use 1,000 to get a really, really close estimate, or maybe we want to use 1,000,000, or maybe 1,000,000,000,000. Maybe let's just not decide how many rectangles to use. Let's just say we're going to use n number of rectangles. We'll pick what number n is later. So the width is just going to be, we have a total length, the interval, the total length is 1. And we have n, we're splitting that up between n number of rectangles. So the width is 1 over n. So this is going to be 1 over n, 2 over n, 3 over n, right? This will just continue until we finally get to n over n. So that's the width of each rectangle. Now what about the height? The heights of the rectangles. Well, the heights are just going to be f of 1 over n for the first rectangle, f of 2 over n for the second rectangle. So this is what we really stressed in the last video. The height of the ith rectangle is going to be f of I over n. So if you didn't watch the last video, quick recap, if you want the height of the first rectangle, you just plug 1 in for I, and you get 1 over n. If you want the height of the third rectangle, you plug in 3 for I, and you get f of 3 over n. That will give you the correct height for the third rectangle. Okay, so we got that down, and now we got to write out our sum. Oh, I also, just real quick, forgot to label this function again, x squared plus 1. Okay, so now let's write out our sum. So this is the sum as I goes from 1 to n now, because we have n rectangles we're summing up, of f of I over n times the width, which is 1 over n. 1 over n. And f of I over n, well, we have a function, so let's plug I over n into our function. And this becomes the sum of I over n all squared, that goes in for x squared plus 1, times 1 over n. So all we're doing is height times width, height times width, height times width. We're just summing up the height of all the rectangles, or the height times the width of all the rectangles, or the area of all the rectangles. Okay, so don't get lost in these i's and n's. It's just area, height times width. Now let's go through our steps to simplify this. So this becomes, as I goes from 1 to n, well, this will become, I guess I have more time, so I'll take my time and do more steps than I did in the last video. So we just square that term out, 1 over n, times, or the whole thing times 1 over n. Let's bring that 1 over n inside. So this becomes I squared over n cubed plus 1 over n. Okay, and now let's break that up into two sums. So again, this is just the algebra of sums that we're doing. And this part is really the easy part. We already figured out the right formulas and everything, so now we're just doing a little bit of algebra here. So this is I squared over n cubed plus the sum as I goes from 1 to n of 1 over n. Okay, and now we know that this sum is just n times 1 over n. So, and you might think, well, wait a minute, 1 over n is not a constant. But it really is, because n, even though we haven't chosen a value yet, n really is just some value. If we choose 1,000,000, this is going to be 1,000,000 times 1 over 1,000,000. If we choose a bigger number, it's just going to be that number times 1 over itself. So no matter what we choose for n, this will simplify to 1. So this whole thing becomes 1. Let me maybe use a different color. This whole thing becomes plus 1. And now all we have left to do is simplify this. And we can, for the same reason that we treat 1 over n as a constant, 1 over n cubed is just a constant that we're going to pull out of the sum. So this is the sum as I goes from 1 to n of I squared. And we already know that formula, but let's remind ourselves once more of what that formula is, because it's definitely going to show up on your test, assuming this is what you're talking about in class. So it's n times n plus 1 times 2n plus 1 all over 6. Okay, so this becomes, let's see, and this is all plus 1. So what does this whole thing simplify to? Well, it becomes, I guess I'll stay with pink, 1 over n cubed times by, well, we just wrote the sum out here, that's n times n plus 1 times 2n plus 1 all over 6 plus 1. Okay, so now we have a really nice, neat, simple expression for our estimate based on the number of rectangles we have. We could choose 1,000,000, we could choose 1,000,000,000,000, we could choose a bigger number than that, we could choose as big of a number as we want. We just plug it in for n and that will give us our estimate. But if we know that the bigger the number we use, the better the estimate, why stop at 1,000,000 or 1,000,000,000,000 or 1,000,000,000,000,000 or anything? Why stop anywhere? Let's instead take the limit as n goes to infinity. And we can simplify this entire expression. N times n plus 1, that's n squared plus n. And then that distributed to 2n plus 1, that all simplifies to 2n cubed plus 3n squared plus n. All over, and then 1 over n cubed distributes to this 6. So that's over 6n cubed plus 1. And now you should know, maybe from pre-calculus or even this calculus course possibly, you should know that this limit is just the ratio of the leading terms, assuming the leading terms have the same exponent, which they do. They are both 3, right? N cubed over n cubed. So it's just the ratio of the leading terms, so it's 2/3, and then the limit of a constant is just that constant, so this becomes 2/3 plus 1. Or in other words, this is equal to 2, I knew something was wrong. Not 2/3, 2/6. So 2/6 is just 1/3, right? 2/6 plus 1, or in other words, 1/3 plus 1. And then that just simplifies to 4/3. And that is the exact area under the curve, which is really, really cool. This exact area here is 4/3. Now let's see how close we got. What is 4/3? It's 1.133, right? Or 1.333, right? 1.333. What is 94 divided by 64? So 94 divided by 64, that was our estimate, 1.46 something. So we were pretty close, using just 4 rectangles. But now we have a way to find the exact area. Now, let's take a look at some interesting things that happen. One is that we took the limit as n goes to infinity. Well, as n goes to infinity, look at what happens to the width of the rectangles. The widths start approaching 0. So as n goes to infinity, these approach 0. So we're making the width of each rectangle infinitely small, and then we're summing up an infinite amount of those rectangles. And somehow that comes out to be this exact area here, 4/3. Oh, that's impossible to read, huh? Maybe this will be better. 4/3. That to me is wild. And you're summing up an infinite amount of infinitely small rectangles, and even though it's an infinite sum, you're getting a number, an exact value, 4/3. That is the area under that curve. That's wild. And oftentimes, just as a liner note to this video, you'll see the limit written out front just to begin with. The limit as n goes to infinity of the sum. It's the same thing. I chose to save it to the end just so that you wouldn't get caught up in the limit part. You could evaluate the sum separately and take the limit at the end. Okay, I hope this helps. See you in the next video.